Alright, today we're going to talk about simple harmonic motion as an extension to what we are doing with springs. Now, one thing I want you to keep in mind with this simple harmonic motion is there's a lot to it. We're just going to look at masses on springs this unit. That's all that's going to be on your test. And then at the end of gravity, we will tack on more instances of simple harmonic motion. The reason I want to spread it out is because this topic, one, comes up a lot on the AP test, and two, is really difficult to get. It's not very straightforward. It's not intuitively obvious. There are a lot of different pieces to it. So we're going to set up some basics today, and then just look at the implications that it has for springs, and then we will move on in our next unit with even more places we can identify and use simple harmonic motion. So, like I said, we're going to look at mass on a spring, on a horizontal spring right now. So I'm just going to sketch that out really quickly. We're going to say that is my mass just at rest naturally. We have no friction on this surface, and that's going to be my equilibrium position. So the first thing we're going to look at is stretching the spring out a distance of A. Now, when we do that, when we stretch the spring out a distance of A, we're going to move that mass, and we're going to let go. Now, looking at that mass, the spring is pulling, there's my distance A, the spring is pulling back on that with a force Ka. Now, the reason there's going to be a negative sign there, and I don't want to be clear on this, the direction that goes with A is to the right, but the force is to the left. And the way that we're going to denote that oppositeness is with that negative sign in front of the K. So, it's being pulled back with F equals Ka. Now, we know that it's going to accelerate from that point and try to get back to equilibrium. But what we're going to say about the spring is that the spring is exerting a restoring force on that mass. So, restoring is the important word here. The spring exerts a restoring force on the mass. Now, what I mean by restoring force is it's a force that pulls the mass back towards equilibrium. Okay? So a restoring force wants to return an object to equilibrium. It wants to restore equilibrium. That's what's happening there. Now, as this thing goes back, it passes equilibrium, and then it swings out to a negative A, stops, and comes back. And the reason it stops there, we'll wait. So the mass moves back to equilibrium, and then it goes to x equals negative A, and now the spring is compressed, so it's pushing on my mass, and it pushes us back to equilibrium, and now we're moving back and forth between those 2 points. So, we're going to look at A, B, and C really quickly, and we'll look at the forces for all of those as we do it. So, the basics on simple harmonic motion is that this mass, my object, is going to oscillate back and forth around this equilibrium position. So we'll label the equilibrium position B. We'll label when we're at negative A, and then positive A is going to be C. So let's look at the forces on my mass at that point. So, at A, force points to the right because I've compressed my spring. The force is negative Ka. The acceleration is negative Ka over m, which shouldn't be a surprise. I have a lot of force acting on there. It is accelerating at that point. The spring is compressed, so I have a potential energy of 1/2 Ka squared. But at that point, it gets to x equals negative a and stops. Because now all of my energy is back into potential. And it's going to slingshot back forward. Okay. So at this spot, my kinetic energy is equal to 0. So looking at each one of these things, I have maximum acceleration at this point. This is when I have the most force acting on me. I have maximum potential energy, and I have minimum kinetic energy. So when I'm all the way out at A, my biggest displacement, maximum acceleration, maximum potential energy, minimum kinetic energy, minimum velocity. Okay. Now the next point at B, let's look at it, and we said that there are no forces acting on it. That is a neutral spring. It's not stretched, it's not pulled out. My net force is equal to 0 there. That's what makes it my equilibrium position. So my acceleration is equal to 0. If my spring is not stretched out at all, my potential energy is also equal to 0. We know that if my potential energy is gone, it had to go somewhere. So all that energy is in kinetic energy. And it's 1/2 mv squared. So all of that 1/2 Ka squared became 1/2 mv squared. So I have maximum kinetic energy at equilibrium, or maximum velocity at equilibrium. Minimum potential energy, minimum kinetic energy. Now, this is always true at equilibrium. When we are at our equilibrium position, our velocity is going to be the highest. That's a really good thing to know and a really good thing to hold on to. We're moving our fastest at equilibrium, and that's kind of how equilibrium works. So, what we know is that my maximum potential energy is equal to my maximum kinetic energy. But they happen at different times, right? Maximum potential energy happened when we were as compressed as we could get or as stretched out as we could get. And maximum kinetic energy happened when the spring wasn't stretched out at all. So I can set those two things equal to each other and hopefully find the speed. 1/2 Ka squared equals 1/2 mv squared. No big deal, very simple. So my halves cross out, and if we solve for v, it's the square root of Ka squared over m. That's my maximum velocity. We don't have to clean it up much more than that. Here's just a simple way to find our maximum velocity. That's a lot of the time going to be a conservation of energy question. But we can only do it at the place where the acceleration is equal to 0. Now, point C, all the way out at positive A, looks just like point B, except for the force points in the opposite direction. And just like at point D, now that I'm out there as far as I'm going to get, my potential energy is 1/2 Ka squared, my acceleration is negative K over m, and my kinetic energy is equal to 0. This is a whole lot like point A. Okay? We're just moving between these 2 points, swapping kinetic and potential energy in between these places. So, what we're going to say in general to expand out from the spring is that any object under the influence of a restoring force moves in simple harmonic motion. And so in general, the force, let's finish that, sorry. And in general, the net force for something undergoing simple harmonic motion is net force equals negative kx. In general, it's going to look like that. And we're going to explore that in general case a little bit more at the end of the next slide. So, any object under the influence of a linear restoring force, any object that has this net force equation is undergoing simple harmonic motion. Okay? If we add in friction, if things get crazy, It's not simple harmonic motion anymore. But this is what it's going to be to define simple harmonic motion. So, we're going to look at the same mass on a spring, stretch it out, it's going to fall back to that position, move between these two A's. So when it's out there, it's going to move in. That's the restoring force part of it. Now, this may be a stretch for you to remember back into pre-cal, but something undergoing simple harmonic motion has sinusoidal motion to it. If I were to graph the position as a function of time, I'm sorry, the force there is equal to negative kx. If I was to graph this function as a function of time, it'd be a simple sine or cosine curve going between a and negative a. Now what we're going to call a and negative a are amplitudes. It's my maximum displacement. Okay? And so without friction, it will constantly move between a and negative a, and it will look like some sort of cosine curve. Now, if we look at 2 points like that, look at one complete cycle, the time that it takes to complete one complete cycle is called period. That's what that capital T is. Okay? So one complete cycle has period T, and we'll talk about that a little bit more as we go on. We talked about it last year when we talked about waves. The period is the time for one revolution. Now, the interesting thing about this, any object undergoing simple harmonic motion, whether it be a mass on a spring, whether it be a pendulum, whether it be the spring inside of a watch bouncing back and forth, is going to have the same graph of its position or its displacement versus time every single time. And the nice thing about this is I know what that function looks like. Okay? I can say that position as a function of time is equal to the amplitude times the cosine of omega t. And this omega t thing is what's going to define how long or how spread out that period is. So that's a simple cosine curve. Now, to define this omega thing, it is the angular frequency of my object. It's a lot like angular velocity, but we're going to call it angular frequency because this thing is moving back and forth. It's completing cycles per second. Now, as always, omega is measured in radians per second. Frequency, as we're used to talking about frequency, is in cycles per second. We call those hertz. It's how many times we go through one complete cycle. So we move from A, way out here, all the way to negative A, all the way back to A. Returning to my starting point in the same motion is one cycle. So the frequency is how many times that happens per second. And the period is how many seconds it takes for one complete cycle. Period is the measurement that we go after a lot. So, what's going to be convenient to get the frequency that we're used to talking about is to convert it between omega and f. And the way that we do that, frequency is omega over 2 pi. That's how I go from cycles per second to radians per second, right? You may have to think back to what we did way back in the beginning. But one cycle is 2 pi radians. So, a frequency of 1 revolution per second has an angular frequency of 2 pi radians per second. This is the conversion factor in terms of frequency. And since the period is just the inverse of the frequency, the period of our motion is going to be 2 pi over omega. That is very good information to know. So, since we're really big fans of calculus, let's look at the velocity as a function of time and see how that changes. We're just going to take the derivative of cosine. Now, I think we've all done that. So the derivative of cosine is negative sine. The stuff on the inside stays the same, and we're just going to multiply that by the derivative of the inside. So it's negative a omega sine omega t. Now we're going to look at acceleration. So we're going to take the derivative one more time. The derivative of sine is cosine. And again, we multiply by the derivative of the inside with respect to time. So now the acceleration is negative a omega squared cosine omega t. Now, this we get just from knowing kind of what the shape of the graph looks like. We're going to take it and put it back in over here for force equals negative kx. Now I know force is mass times acceleration. So let's just substitute that in there. ma is equal to negative kx. Well, I have an expression for x and I have an expression for a. So let's go ahead and solve for a. A is equal to negative k over m times x. Now, the College Board likes to call this the differential equation that describes simple harmonic motion. So the way that we're going to do it is say that acceleration is the second derivative of position. So the acceleration, another way to write that is d squared x over dt squared. And then still that's equal to negative k over m times x. So just as a note, this is the differential equation for simple harmonic motion. Sometimes the College Board wants you to do that. And as always, just like falling through a resistive medium, we started with force equals ma. ma equals the net force. And then we pulled that down until we got to a differential situation. Well, the nice thing is, we know what to put in there, right? We're going to take the acceleration and the acceleration function that we have down there, substitute the function, and then substitute the function for position. So, for the acceleration we have negative a omega squared cosine omega t is equal to negative k over m times my x function, which is a cosine omega t. Now, right away you can see that some stuff's going to cross out. The negative sign goes away. A goes away. And cosine omega t goes away. So it's telling me something very important. Omega squared is equal to k over m. Now, that's going to be very important for determining our period. Okay. And that stuff on the inside of the cosine omega t, sine omega t thing is what determines how quick or how small that period is. And what we've just done is show that that really depends on the mass we have attached to our spring and how stretchy my spring is. So if we look at the period in terms of this, period is equal to 2 pi over omega, which would be times the square root of m over k. If you look on your formula chart, that is the period of a spring in the formula chart. This is where it comes from. Now, the College Board doesn't necessarily make you go through this entire process, but what I want you to know from this and what they expect you to know from this is the general case. So for my general case, we have the second derivative of a function equals that function. So we have a equals negative k over m times x. A is the second derivative of x. I just wrote it in a different form. The thing that's between the negative sign and the x is our omega squared, which is going to determine our period. This form in blue right here is super important for you to know and to carry out as we see different situations of simple harmonic motion. I will show you a few of these, but the College Board does like to throw curveballs. So, we need to remember that stuff in blue as the simple harmonic motion condition. That is what we need to take away from this. The energy stuff that we did on the last page is super important. This is also super important. Understanding how to get that omega term from a force equation. We need to be able to do that.